Wasabi, you guys. In this video, we'll be doing part 2 of the Integration B training for beginners. This time, we will be doing working with U-substitutions. Now, I'm going to warn you a little bit. I will be going fast. Okay, I'm assuming that you have taken Calculus 2, and so this is kind of like a review in a way, but I will be going fast-paced a bit because we have a lot of integrals to go through, and yeah, we have a lot of integrals, so I will be faster paced. So I'm going to assume that you've taken Calc 2 and that you're aware of this. I'm just giving you kind of a good review. All right, so let's get into the U substitutions. Now, first, we're going to go ahead and start with this easy integral. Right, so now we have constants like this. Then we can say this is just the integral of cosine and sine, but because of that coefficient, we divide with that coefficient, and so this is our integral. Okay, so kind of like the derivative where you multiply, this time we divide because we're integrating. So we are dividing the constants. Okay. Next. So the trickiest part maybe, but this is probably a good habit for beginners, is to identifying their u and their derivative, their du, right? So in this case here, what would be the u and what would be the du, right? In Integration B, you need to learn how to detect that immediately, like fast. So in this case here, we know that x squared, the derivative of x squared is x here. Cool, so we can do u equal x squared, and our du is equal to x dx. So our x can be replaced. I mean, not replaced. So our x is, so this is gone. So now we have e to the negative u du. And so now we have e to the, this is just negative e to the negative u. And then just plug back in u. And this is your answer. Oh, I lied. No, it's not. So, you see how I went very fast? I went very, very fast, a bit too fast. This is what happens when you integrate way too fast. You forget the small things. The derivative, you probably already catch this. If you caught this, very good job on you. You are very careful. So, 2x, it's 2x. So this is, we have to divide that too. So it's a half. That x dx gets substituted. E to the negative u. So our actual answer is this. All right, cool. Almost died. We almost died, but we caught it. Okay. X cubed x4 minus 5. Now you're probably thinking, oh, I see the derivative. Let u equal x to the power of 4. Now, this is just a constant. It's just a constant. So because this is just a constant, most of the time it's nice to have it with you, so that the du, because the constant, I mean, if you derive a constant, it's just 0. So your du is 4x cubed dx. Okay, that 4 gets divided, 1/4. Du, and then that whole, instead of u minus 5, you just get that whole u all to yourself. And now this is just 1/4 ln of u. And that u is x4 minus 5. Okay. Next integral. All right, let's keep going with this. Let's keep getting used to it. All right, we're going fast. All right, this is just a linear polynomial. We could just u sub that whole thing, no problem. U equals 2x minus 1. All right, then du is equal to 2 dx, so that 2 just gets divided. All right, and then we have that whole u to ourselves, du, right? One of those integrals that we memorized. This is x 3/2, 2/3. You can simplify this, I guess. So this becomes 1/3 plus c. Okay? Oh, what am I doing? No. Why is it in terms of x? I don't know why it's in terms of x. Let's see, this is what happens when you... Oh god. Oh god. Don't go too fast like me. I'm so used to being fast. It's not a perfect habit. U is equal to 2x minus 1. Ooh. Again, we're almost... You see how this can be tricky? Solving an integral regularly is an entire different story than speed integrating. So, be very careful. Be very extremely careful. Okay. Cool, so we got this. On to the next integral. Alright. How about 1 minus x to the power of 9 dx? Right? Thank goodness we have U-substitution. Otherwise, this would be ugly. Right? Expressing this, no thank you. Thankfully, this is a linear polynomial, so we can let u equal 1 minus x. Right? Don't forget that du, this is negative dx. So we have a negative u to the power of 9. Okay? And so now we can go ahead. This is just this. So our answer is 1 minus x to the power of 10 all over 10 plus c. Okay? Cool. Next is integral dx 5 minus 3x. So this is one of those integrals that we memorized, right? So this is a negative 3. I don't know why I wrote it like that. Negative 3, negative 1/3, and then the ln of 5 minus 3x plus c. From the previous videos we had, it was one of the types of integrals that we must have memorized. Right? If you were to competing like head to head, like this will literally save you. Like a head-to-head integration bee tournament. Cosine cube, sine of x. Okay. Again, it's so important to memorize all your derivatives. So we have let u equal cosine of x, so that du is equal to negative sine of x. Now what we have here is negative u cubed. So now this is negative u4 over 4. So now this is negative cosine, cosine to the power of 4 all over 4. And we got that answer. Okay. Let's keep going. E to the x, 1 minus e to the x square. Ooh, what do? Do we express this? Of course not. Take advantage of this, right? U is equal to 1 minus e to the x. The reason why this is good is because our derivative is e to the x. well, negative e to the x. But, I mean, that negative, it doesn't harshly affect us because we treat the negative like it's a constant. So, we're technically safe. And then this is 1 over u from the from our memorization video, and then this is just 1 minus e to the x plus c. Okay. Let's keep developing our U-substitution senses. Okay. All right. Oh, this looks familiar, right? U equals square root of x. We memorized that this is 1 over 2 root x dx. Okay, so because of this, again, this is a half, so we reciprocate it here. It's not a half, it's a 2. Okay, because this is a half. So we reciprocate it. So be very careful with that. We reciprocate it as a 2. So now that square root of x cancels out with this. So we have sine of u du. This is negative 2 cosine of u, which gives us negative 2 cosine of square root of x plus c. Okay, next integral. ln square over x. Aha, I let u ln of x, so that du is equal to 1 over x dx. Right, okay, cool. So this is just u squared. Okay, so again, 1 over x cancels out. We just have it in the u world. And then we have our answer. So the more you keep doing U-substitution integrals, you'll actually develop like a mental, you start solving these mentally. Experience, lots of experience, lots of practice. You just have to get used to it. Right, but definitely memorize your derivatives. Otherwise, this would be nearly impossible for you to be fast at. So this is crucial. All right, what's our u here? Our u is equal to cosine of x, because cosine of x is inside here, inside a function, and our du, our derivative, is outside here, which we can cancel it out with. But this is negative sine of x. Okay, the derivative of cosine of x is negative sine of x. Okay, so we have a negative integral sine u. This is equal to, let's see, if we integrate this, it's the integral of sine of u is negative cosine. So the negative cancels out, so we get cosine of u. So our answer becomes cosine of x plus c. All right, so now we've reached to a point of just a little bit of advanced cases. Just a little bit of advanced cases. Okay, so I'm gonna slow down a little bit here. All right. So what do we do here? Okay. So radicals like this, I like to have something, have a u inside here, right? So that this becomes like, we can make this into a power rule type of integral. So let me demonstrate. U is equal to x plus 2, right? And then du is this is just dx. So we don't have to exchange anything back. Now, the reason why I'm saying this is, the derivative of x plus 2 is just 1. So du is equal to dx. However, what do we do with this x? What happens is, because we let u equal x plus 2, u minus 2 is equal to x. And so this becomes u minus 2 and the square root of u du. Now you go ahead, apply power rule, and then you do your own thing, u5, 2, 5, minus, let's see, this is 3 halves, thirds, and then let substitute your u. U is equal to x plus 2. And that's it, and then you have your answer. Okay? So, a little bit tricky to see, but again, you just have to keep doing it, and then you'll get the hang of it. Alright? How about the integral of x squared plus 1, x cubed plus 3x to the power of 4 dx. Express this? Hell no. That is nasty to express, right? So, but can we do a U-substitution? Can we actually? What's my U? What is my U? Right? So, you would think, ooh, maybe our U could be in here because of that power of 4. But what about my du? Is my du of this out here? Right, so if you want to check, you can, right? Let u equal x cubed plus 3x. Then deriving this, we get 3x squared plus 3, right? Is my du out here? X squared plus 1. Ooh, what is this? It is out here. So, we just have to divide 1/3. Okay, so x squared plus 1, that gets taken. So we have u to the power of 4 du. And now we have u to the power of 5, 15. So this is now x cubed plus 3x, all to the power of 5, all over 15 plus c. Secant square, tangent square. You're probably thinking, oh, maybe simplify this in terms of sines and cosines. Well, actually, or you could just leave it like this. Let u equal tangent x because du is equal to secant square. So we could just take that and take advantage of it, and we get this integral here. So we get du over u squared. This is negative 1 over u. So we have negative, let's see, 1 over u. This is just technically cotangent x plus c, and you're good. All right. How about cosine 2x minus 1? All right, what do we do now? I'm just kind of joking with you. The u is 2x minus 1. This is a linear function. We could just take that and, let's see, 2x. So remember du is 2 dx, so we have to divide that too. Cosine of u, this is equal to a half of sine 2x minus 1. All right, let's get a little bit tricky. Cosecant square, and the square root of tangent x. All right, what do we do? What do we do? Okay, so in your brain, you should already thought, well, the derivative of something that equals to cosecant square right? What is we know something about that. du is equal to cosecant square. That's what? That's u equals well, technically if you this would be negative cotangent x, but we kind of want to sort of, I mean, negative, we treat negative as a constant. So technically, if you just to do u equal cotangent of x, then du is equal to negative cosecant square. Now, but where's our cotangent? Well, you have your tangent here. This tangent here could become cotangent. So what this means that this would equal to cosecant square root of cotangent x. So we do this so that we can make a good U-substitution just to get rid of this with our du. So now we get a negative integral square root of u. All right, and then just like this is one of the integrals we memorized. This is 3/2, 2/3, c, negative 2/3. U is equal to cotangent x, 3/2 plus c. All right, what's our u and what's our du? Our u can be e to the x plus 1. We want our u to be down here so that it's just easier to manipulate. But this is just an ln type of integral. So u is equal to e to the x plus 1, du is e to the x. This is simply du over u. This is ln e to the x plus 1. Sine of 2x, 1 plus cosine square. Whoa. What do we do here? What's, I mean, we see cosine, it's like, it's being squared. Let u equal cosine of x with this help. But then we need, if we're going to make that substitution, we need a sine of x. Ignore the negative, because the negative is a constant, so we could deal with that later. But we need a sine of x, right? We have sine 2x. If you remember your trig identity, this is 2 sine of x cosine of x, then 1 plus cosine square. Oh, okay, yeah, this would work, because that sine of x, we can cancel that out, and everything would be in terms of u. Cool. All right, so we do it, do the substitution, negative 2, we get u, 1 plus u squared, 2u. Okay. Now what? That's not inverse tangent. We have a u on top. So what do we do? You can do another U-substitution. You can do another U-substitution. Oh, that reminds me. That actually reminds me. I don't know if I included this in the 10 derivatives you should have memorized by heart. I don't think I put this in the list, but I'll continue this further, and then I'll show you. I'll share it to you after this integral. So we have 1 plus u squared dw. It's 2u, which technically, ironically, we have it right here. 2u's right here. So negative dw, w here. So we have negative ln of w, which is 1 plus u squared, which is u is cosine plus c. Okay, now what was I talking about? Yeah, I'll go like this. I can't believe I forgot this. But the derivative of sine squared, this is a bonus. This is a bonus. It's one of those things where like derivatives that you must memorize by heart for integration B. And surprisingly, I didn't include this. So if you made it here in this video, this is your checkpoint prize. So the derivative of sine squared is sine 2x. Okay, sine squared, the derivative of sine squared is sine 2x. Now, why? The reason is because chain rule, right? This is a chain rule, sine squared, bring the power down. The derivative of the inside is sine x. And this is the same thing as sine 2x. Okay? So, the fastest way, so the actual fast way for this integral is actually u equal 1 plus cosine square, so that du, well, 1 is just 0. But if you do cosine square, then you get negative 2 cosine x sine of x. Right? That negative comes from cosine of x, because cosine of x, the derivative of cosine of x is negative sine of x. And this is negative sine 2x. And so we get negative. So here we went straight on to here. And then, this is negative ln of 1 plus cosine square plus c. Okay, so that's a bonus. Very good derivative to memorize by heart. Integrate cotangent of x dx. I feel like this is one of the integrals that you should also memorize by heart. But if you forgot, that's okay. You can turn it in terms of cosine x sine of x. And this is just a U-substitution. Let u equal sine of x. And du is equal to cosine of x. Okay. Remember that the du has to be on top or outside. Okay. It cannot be reciprocal. You cannot have like a reciprocal du. Like you can't. No, your du cannot be reciprocated like that. Okay. So meaning like you can't have a cosine x. If cosine x is right here, you cannot do the substitution. Cosine x has to be on top. Okay. But other than that, you have 1 over u du. This is just ln sine of x plus c. This is the integral of cotangent. Okay. Very helpful to get this memorized by heart. Next up, cosine of ln of x over x. Right, so again, as soon as you see this, you should have immediately noticed that, let u equal ln of x. Because du is equal to 1 over x, and we can use that. And we can just, okay, so this is now cosine of u du. This is sine of u, plug in u back, ln of x. That's your answer, right? So again, we're doing this fast. You know, it's very good to solve basic U-sub integrals like this. It's good to like learn how to sort of solve it half mentally a bit, right? The most important is detecting your u and your du. x4 plus 1. Okay, so what's my u and what's my du? Alright, so I definitely cannot do u equals x4 because that requires an x cube. that requires an x cube. We do not have an x cube. So what do we do? Right. So here's an integral to, here's a process to sort of memorize. So we can't do u equals x4, but what we can do is we can let u equal x squared, so that du is equal to 2x dx. Now, I don't know if this is going to come out good, so let's try it, right? Let's try experimenting it. Let's just try it. Let's test it out. Okay, so then my du, we have a half integral. The x gets canceled out. So du, we have x4, we have x squared, so this is u squared plus 1. Oh, this works out nicely. Why? Because this is just inverse tangent. Okay, cool. So we have inverse tangent of u, which is x squared, plus c, and you're done. Cool. This. All right. Now, not everything is about substituting, right? Now we've gotten to a point of sort of a little bit of strategizing, right? What do you see here? Well, what I see is we can actually split this. We can split this because if I split it, this is just inverse tangent, and this is just a U-substitution. It's just a U-substitution. So we're good. So inverse tangent of x, and then here let u equal 1 plus x squared. Du is equal to 2x dx. And so now this integral here becomes 1/2 of du over u. Oh, okay, and this is ln. Okay, so 1/2 is ln of u, which is x squared plus 1. And we have our answer. Okay, again, splitting is still nice. Splitting is still nice, right? It's about knowing your derivative and your integral, and then knowing your u sub cases. Oh, this is a du. My u can be, so learning to detecting that is very crucial. Ooh, let's get a little trickier. Okay. This is going to be a bit difficult to see. What is my u and what is my du? So we have a little trouble with this. Right, let u equal x squared plus 1. Okay, because it's inside the square root. But then our du requires 2x. So it needs an x. We need an x. Right here, what we have is x cubed. Oh no, we're in trouble. We have an x cubed, not an x. Well, technically you do have an x. It's just kind of camouflaged. Right, so in a way, x cubed is x times x squared. And you're probably thinking, okay, but what about this x squared? Our u is equal to x squared plus 1. That's okay, because that u is equal to x squared plus 1, x squared is equal to u minus 1. So, oh, okay, so then we're good to go then. All right, so we have our x, we have x squared, we know what to do. Okay, so we're good to go. Half x squared is u minus 1, square root of u du, right? And this is just power rule. So this comes into I'm just gonna go ahead and do this quickly. But you know what to do next here. Like it's just power rule here. And you should end up with this. And that's it. 0 to 1. Cube root of 1 plus 7x. Oh god, what do I do? What do I do? What's my u? What's my du? Well, my u is just 1 plus 7x. This is okay. We can do whatever we want because this is a linear function. So that's very nice, which means we could just plug in our u here, our du, which is it's just going to be 7 dx. So we just have 1 over 7. And then we have a cube root of u, du. Wait a minute. Wait, but what about our bounds? What about our bounds? What do we do? So the way the bounds work is you plug in the bounds to our u sub. So what would this bottom here and what would this be top here? So our bottom here is going to be 0 plugging in to x. Okay, so plug in 0 for x, so plug in 0. This is 0 plus 1, so 1 is here. All right, next, plug in 1 here. So grab this 1 and plug it here. Okay, x equal to 1. That makes it 7. 7 plus 1 is 8. Okay, so it's 8 on top. So that's how it works for U-substitution. Okay, so then continue. 1/7. This is, all right, 1/3. Put it in power rule. 4/3, 3/4. 1 to 8. Okay. Put the constant. Plug in 8. 8 cube root of 8 is 2. 2 to the power of 4 is 16. Divided by 4, that's 4. Times 3, that's 12. Minus, and then plug in 1. It's just 3/4. And honestly, you can just leave your answer like this. Unless it's like Scranton University, then RIP. Integrate from 1 to 2. E to the power of 1 over x. X squared dx. Aha. Alright, what now? Again, and one of the derivatives that we have to memorize by heart. And that's u equal to 1 over x. Then our du is equal to negative 1 over x squared dx. And we do have an 1 over x squared here, right? It's our reciprocal. Awesome. So now we have so this would be negative. And then we've got our du. So it's just going to be e to the u, du. Easy peasy. Don't forget that you have bounds. Okay, do not forget that you have bounds. So we have 1, and then plug in 2, plug in 2 here. That gives us 1/2. Oh, this looks awkward. Huh. This looks very awkward. We have the bigger number at the bottom and the small number on top. Well, that's what this negative is for. That's what that negative is for. So that negative, what happens, how it works is that negative can switch those bounds. This negative will reverse the bounds. Okay, so now that it's negative, it becomes positive. Oops, positive from 1/2 to 1. E to the u du. Okay, so that negative switches the bounds. Okay, that is also a very useful trick to be aware of. Okay. Yeah, so you can't just switch the bounds freely. That's not how it works. No. If you want to do that, you have to add in a negative. In this case, the negative kind of cancels it out. So we have this. Cool. And this is an easy integral. It's just e to the u. So 1/1/2. This all equals to e minus e1/2. Okay. The reason why we don't have to plug u back in is because we have these bounds that were already solved in terms of we already plugged it in into x. So because of that, we don't have to plug back in u. We could just input it. That's why we changed our bounds in the first place, so that we can go ahead and go straight into evaluating. Whew. Negative pi over 4. Pi over 4. Alright. X cubed plus x forward tangent of x. So what's my u and what's my du? Ha! I am indeed fooling you. So, if you do not remember from the first part, our previous video, symmetry. Aha. So, this is symmetry. I notice it's very sus to see that we have a negative pi over 4. Very sus. Okay. That means, is there an odd function here? This is an odd function. This is indeed an odd function because we have an even function times an odd function, which is an odd function in total. So, that means that this whole integral is equal to 0. Okay, that is equal to 0 by symmetry. Do not forget that beginner trick. Otherwise, you'll be wasting your time solving overly complicated integrals. 1 to 2, we have x square root x minus 1. It's that similar trick that we saw before. Inside the square root, we want to substitute that, let u equal x minus 1. Du, the derivative of this, just 1, so it's just dx. But there's x hanging, that's okay. We can solve for x, substitute x is equal u plus 1, right? Because we bring that minus 1 to the other side. So, okay, so then we just plug that in. All right, so this is u plus 1 square root of u du. What about our bounds? 1, plug in 1, that's 0. Plug in 2, 2 minus 1, that's 1. Okay, cool. Awesome. So then this is just, and then power rule, distribute and power rule. I'm just going to go by fast for the sake of time. This is 0, that does nothing. 1, it was just coefficients. So your answer should be this. 5, 3, x4 sine of x dx. What is this? This is equal to 0 because this is an odd function. And it is very sus to see that it's negative and positive here with the same value, just opposite signs. This is equal to 0 by symmetry. Okay, reminding you again with that trick because it is so important, you cannot forget it. E4 x square root ln of x. All right, what's my u? My u is ln of x Why? Because du is equal to 1 over x, and we have a 1 over x right here. Okay, cool. So my du will have square root of u. Okay. Here, plug in e, ln of e, that's 1. ln of e to the power of 4, that's 4. Alright. And then one of the derivatives that we memorized, so when we integrate this, don't forget about that 2. So it would be 2 root u. And then plug in 1, 4. Okay, it's the square root of 4, that's 2. Square root of 1, it's 1. So the answer we see, this is 2. Next integral is from 0 to 2. We have x minus 1, e to the power of x minus 1, square dx. Alright, what's my u sub? Well, it seems like we have a composite function of x minus 1. So u is equal to x minus 1. Du derive this, it's just 1, so it's just dx. Okay, so we have u squared du. Okay, cool. And then our balance is what? Plug in 0, you get negative 1. Plug in 2, 2 minus 1, it's 1. Alright, what do we do? Another u substitution, right? Let w equal u squared. Wait a minute, stop. Stop right there. Stop right there. I think you nearly forgot. You nearly forgot something. Nearly forgot something. What is this? Yeah, the balance is very sus. We have negative 1 from 1. Is this an odd function? This is even. And, ooh, this is an odd function. This is an odd function. Okay, this is an odd function. So this is equal to 0. Oops, there we go. This is an odd function. Okay, this is a great example of what an integration B problem would look like. Okay, so be very aware of symmetry. Be very aware of symmetry. Okay, that's what a symmetry would look like when it's hidden. So, good u substitution, and then symmetry. This all equals to 0. From 0 to 1, e to the x plus 1 over e to the x plus x. What's my u? Oh, so u is equal to x plus e to the x, right? Because you would mentally develop, you'll have that habit of mentally seeing, oh, well, if I derive this, it becomes this, which is exactly what I want. U is equal to x plus e to the x. Du is equal to 1 plus e to the x, which is what we have here. Awesome. So this is just du over u. Okay, and then you plug in the bounds. You plug in the bounds, which gives us, let's see, plug in 0, you get 1. Plug in 1, we get 1 plus e. So we get ln of u, 1, e plus 1. Okay. Don't forget that ln of 1 is equal to 0, so this is just ln of e plus 1. How about from 0 to 1, 1 minus x squared. Alright, so this is not a u substitution trick. Okay, this is not u substitution. This is an entirely different concept, and I want to bring it here because in some u substitutions, in integration B, sometimes u substitutions can lead us into this position. So whenever you see something like this, I think I should write it in a general way. we write it in a general way. I'm going to call this r squared minus x squared from negative r to r. Okay, so the reason why I'm calling this r is because if you graph this function, any function like 4 minus x squared, or 9 minus x squared, or 25 minus x squared, these are functions of what? What are these? What are these functions? These are like circles. They're like circles, except that it's a semicircle, right? It can't go like this. It can't go into a full circle because otherwise that's not a function. But that's what these functions would look like. It would look like this. And this is a radius. Okay? So, the reason why I brought this up is because now that this is r, this function looks like this. So it's a circle with the domain negative r to r, right? So it has to be exactly in this structure where r squared is here and the bounds are the radius. So radius square inside the radical, radius negative to positive into the bounds. I'm sorry. Well, it doesn't have to be exactly negative r to r. As long as the bounds have radius numbers, then you're good. But you'll see what I mean in further detail. So here, because this is negative r to r, this is the area of a semicircle. So the area is pi r squared half, right? Integration is about area. So technically, this whole integral is pi r squared half, right? But what we have here is it's 0. So what do we do? What do we do with that? Well, excuse my tiny eraser, but if this is 0, then okay, that's whatever. That's kind of whatever, right? R0 will just be cut off here, right? So then the domain here is a graph, is 0. Then this area, what will this area be? It's just 1/4 of a circle. It's just 1/4 of a circle. This is pi r squared divided by 4. So now this is now pi r squared 4. So whenever you see something like this is like a partial circle function, right? So whenever you see something like this is an area of a partial circle. Area of a partial circle. In this case, we have 0 to 1. Because we have 0, this is equal to a 1/4 of a circle. The radius is 1. So the radius is 1. All 1 squared is 1. So our answer is just pi over 4. Okay? So that's this would be our answer. It's an area of 1/4 of a circle with a radius 1. Okay, this is just pi over 4. Right. So same case here. If I gave you 4 minus x squared, or actually, like let's say 121 minus x squared, right? Oh, this is kind of sus. That's a square number. It's kind of sus. Okay, and then we have 0 to 11. Oh yeah, this is a circle. This is the area of a partial circle. Because it's 0, it's 0, right? 0 to 11, right? So we have 1/4 of a circle. So this is divided by 4, pi 11 squared, or 121 pi. I should probably, that's going to annoy the hell out of people. 121 pi over 4. There you go. That would be your answer. Okay. Cool. I didn't add this to my list, but I'm going to show it to you anyways. I think MIT did something like this, but it was 12 minus 3x squared. Okay, I'm going to throw this at you. And this is -2 to 2. Right, so this is what an integration B probably look like. This is from MIT, integration B. So, very weird, right? So this looks very weird. What do we do? Well, to turn this into, to check if this can be formatted into an area of a partial circle, we want this 3 to be isolated. What I mean by that is we want this to be x squared itself rather than 3x squared. So to do that, we go ahead and divide 3. So or technically factoring out 3. So we're going to divide 3 here. Okay. So we're factoring out 3 here. So divide 3. So that's x squared. 12 divided by 3. Then again, we technically factored out square root of 3. Okay. Oh, what is this? What is this? Square root of 3, -2 to 2. This is 4 minus x squared. Oh my goodness. 2 squared, 2, 2. It's an area of a partial circle. So this is equal to root 3. Okay, and then this is pi times 4. This is from -2 to 2, so it's the area of a half circle. So our answer is 2 root 3 pi. Okay, this is what an integration B problem would look like. Okay, so instead of using trig substitution, instead of using a long trig substitution, we can just dive into the area of a partial circle. Awesome. Well, how about this one? What do we do now? What do we do now? This is also an integration B level integral. So again, this all of this looks very sus already, right? So let's go ahead and split this in 2. So we have x 4 minus x squared plus -2 to 2 4 minus x squared dx. Okay, so yeah, this whole thing looks sus, right? -2 to 2. Oh, wait a minute. So it's an area of a partial circle, right? Okay, I know this. We know this. We learned this. There's an area of a partial circle. This is pi times r squared, which is 4. This is from -2 to 2, so it's a half circle. Okay, so this is equal to 2 pi. Okay, but this one has an x on it. What do I do here? What do you realize? What do you realize what this is? Yes, this is an odd function. This is an odd function. It's an odd function. This is equal to 0. 0 plus 2 pi? Easy. The answer is just 2 pi. Okay? Very, very sneaky. All right, I love the symmetry. I love the symmetry. It's very fast, very helpful, very easy, but it can be blindly not spotted. Okay. From 0 to 1. All right. So what was this video about? This video was about U-substitution. So going back, what is my u? Well, we can't do u equal x4 because we need an x cubed, right? Oh, this reminds me of that last integral, the previous integral that we did, right? It reminded us the previous integral that we did before. Not the previous, but like some very past integral that we solved, right? It's the same trick here, right? So what did I do? I let u equal x squared. And then du is equal to 2x. So this was a half. And then the x gets taken by the du. And then this becomes, well, x4, but u is equal to x squared. So x4 is u squared, then du. Okay, cool. Now, plug in the bounds, plug in 0, that's still 0. Plug in 1, 1 squared is 1. Okay. Oh, whoa! This is an area of a partial circle. Okay, so our radius is 1. So this is equal, let's see, a half. So that we don't ignore that constant. All right, now the area of a partial circle here, this is 0 to 1. So it's a 1/4 of a circle. It's a quarter of a circle. So this is pi. My radius is 1. So it's, times 1. And then divide by 4. So my answer is pi over 8. All right. Very nice. So we have negative pi over 4, pi over 4. We have x4, tangent of x, 2 plus cosine of x, dx. Ah, you already knew where this is going. Yes, you're right. This is equal to 0. You already knew. As soon as you saw the bounds, then checking if this was an odd function, this is indeed an odd function. It equals to 0. Yes. Yes, it does. Ah, see, so I got you. I got you hyper aware now. That's very good. 1 plus over x squared dx. Okay. So what do we do? Now, I'm throwing this at you because you don't always U-sub. Okay, I just want to throw this at you. So, from our previous video, basic integration, we just go ahead and express this. Okay, 1, 2. This is put this in exponent form, and then square root x. Right. So I just square this. Okay, and then this is just all equal to, this is power rule. So we go ahead. So 1 over 4 plus 1 is 5/4. 8/5. For the sake of time, 3/2, 2/3. Right. From 0 to 1. 0 is just 0, so we can ignore that. 1 is just all coefficients. That's 1 plus 8 over 5. It's 2/3. And we're good to go. Okay? I just want to throw this at you. So don't overdo it. Don't overdo it. I know you probably thought, look at this integral, and you're thinking about, what would be my U-sub? No. Just express it. It's just a basic integral. Don't overdo it. Express it, square it, and then, just integrate it regularly. 1, this is x squared plus 1 dx sine of x. All right, what do we do now? Equals to 0. It's an odd function. It's symmetry. 0 to 1, e to the x, 1 plus e to the 2x. So what do we do? This is a U-substitution. We see if we let u equal e to the x, du is equal to e to the x dx, which is what we have here. E to the x is right here. That's good. So we can go ahead, put that there. Du 1 plus, it's e to the x is, so u is equal to e to the x. So this is u squared. Okay. And now, let's see, plug in 0, we get 1. Plug in 1, we get e. Okay. So now, I should have put infinity. This is equal to inverse tangent of u 1 to e. Inverse tangent of e, you could just leave it because there's no simplified form of that. Minus inverse tangent of 1. Inverse tangent of 1 is pi over 4. So that's very easy to know because root 2 over 2, root 2 over 2, root 2 over 2, root 2 over 2, so that's root 2 over 2 over root 2 over 2. This is clearly 1, and this happens at pi over 4, because at pi over 4, sine pi over 4 is equal to cosine pi over 4. So that causes tangent pi over 4 to equal to 1. So inverse tangent of 1 is pi over 4. Okay. Now, the reason why I wanted this to equal to, what was I talking about? I wanted it to be infinity because I can just demonstrate that to you right now. Why did I want this to be infinity? Because the answer would be, well, you know what? Let me just show you. Okay. Let me just show you. Okay, so we know this. We know this. Okay. What is our bound? Plug in 0, that's 1. So if we plug in infinity here, right? Let x equal infinity. E to the infinity, that's what? Infinity. So infinity is still here. Okay. And then we know this is inverse tangent. So the inverse tangent of infinity, it's one of these limit properties that we all should know, and that is the inverse tangent of infinity. That is equal to pi over 2. Okay, because tangent of pi over 2 is equal to infinity. Okay, so inverse tangent of infinity, that's equal to pi over 2. And then minus inverse tangent of 1, that's pi over 4. So then in this case, it would be pi over 4 as an answer. Okay, which is a lot cleaner answer. All right. Let's go. We have 3 left. 3 integrals left. Huh. Interesting. What do we do? I want to try u equal x squared plus 4x. Then my du becomes the derivative 2x plus 4 dx. Huh. I have x plus 2, and if I factor this, that's what it looks like. Aha. So, when we substitute this, we have that 2, so it's a half. The x plus 2 cancels out, so we have our du now. We plug in u. Awesome. So, this integral is equal to, oh, well, that 2 is going to cancel out. So this is just square root of u, square root of u. So now this whole integral is square root of x squared plus 4x plus c. e to the square root of x, dx. All right. Again, memorize our derivatives, and that was, one of them was square root of x. Then du is equal to dx, 1 over 2 root x. Okay, so this time, because it was a half here, it's a 2 here. And then e to the u, that square root of x gets canceled out by du. So now our answer is 2 e to the u. So that's 2 e to the square root of x plus c. Awesome. Last one. Last integral. That is x tan x, 1 plus secant x. All right. What do we do? Oh, let u equal secant of x, because du is, oh, again, don't forget, this is just a constant. Don't be afraid. Don't be afraid. We could just bring that constant in. It won't hurt. Plus 1. Derive that. That's just 0. So it's still going to be secant x tangent x. Okay. Don't be afraid of that constant. Just bring it in. You could just bring it in, and then it'll kind of make our life easier. So secant x tangent x, that's what we have here. So that gets canceled out with du. And then this whole bottom is u. Awesome. Very clean integral. This is just ln of u. Plug in u. This is secant x plus 1. And that's it. Wow. We solved literally 41 integrals. That's very good. That's all of the U-substitution integrals. Cool. So again, we went by that very fast. Even though it's a long video, we went by very fast. It was fast-paced. Again, I'm assuming you've taken calculus 2, but the U-substitution, you have to be very comfortable detecting u and du. And in integration B, if you want to do like speed integration, you gotta learn how to detect that very fast. So again, just keep doing U-substitution problems, or I don't know, I guess restart this video and do the same problem again, except that you try doing it yourself. I don't know, but yeah, a lot of practice with U-substitution. The more you keep doing U-sub integrals, you will mentally develop a sense of U-subbing it in your head, and that's a very good thing, because then you can do U-sub integrals like this. Very easy. It'll become very easy to you, and you'll slowly start to sort of solve these integrals mentally in your head, without writing it out. You just solve it in your head. Oh, I know what to do, and then just straight up write down the answer. So, and that's fast, right? That's what we want. Very, very fast. So, this was a very good U-substitution practice. Our next video, we will practice on integration by parts. Again, it will be fast-paced. Assuming you've taken Calc 2, so this all would be review. The only difference is I'm teaching you how to be a little bit faster, and some other techniques. I hope you find this video helpful and fun. And yeah, thank you for watching, and I'll see you guys in the next video.